Yes, all of you mark your attendance first, and we shall start within a minute. Okay, I hope all of you have marked your attendance. Now let us start. In the last class, we have been discussing about the um, memory mapping functions related to the cache. So, one of the simplest memory mapping function for the cache is the direct mapping. So as we discussed in the direct mapping, a very simple formula is used, that is I is equal to J modulo M, where I is the cache line number. So there are number of lines in the cache. So in which particular line that block is to be transferred. So that particular line number can be obtained in this particular fashion. J is the block number of the block in the main memory, and M is the number of lines in M is the number of lines in uh, the cache. Okay, so using this simple formula, it can be obtained. So if there are m number of lines in the cache, then in that case cache line 0 can be assigned to any of the block which is required in the cache, that is 0m, 2m, 3m, 4m, like that. Whereas line number 1 can be assigned to the blocks which are there in the main memory at the location 1m plus 1, 2m plus 1, and like that. So from this it is clear that only one of these particular blocks can be there in the cache memory. That is either a block number 0 can be there in the memory, or block number m can be there in the memory, or block number 2m can be there in the memory, and like that. Okay, in the case if block number 0 is there in the cache, okay, and if block number m is required to be if CPU needs block number m or 2m, then in that case block number 0 is to be removed from the cache line 0, and there the required, that is either m or 2m block, or block number m or block number 2m is required to be loaded in the cache line 0. Okay, so a single cache line is shared by many of the blocks from the main memory. Okay, so how this is done, how CPU does this is like this. Uh, you can see that the main memory, as you know, is divided into number of blocks. The cache memory is also divided into the number of block locations. They are called the lines, and these lines you can call it as L0, L1, L2, L3, like that. So Lm minus 1, that is m number of blocks are there, whereas the blocks in the main memory, they are labeled here as B0, B1, B2, BJ, and so on. Okay, so large number of blocks are there in the main memory as compared to the cache, the number of lines in the cache. Now, whenever CPU needs to read, that is, CPU needs to work with some memory, so the memory access is either for fetching the instruction, or it may be for reading the data, or it may be for writing the data. So all these accesses, they are referred to as the memory accesses, and there is a memory address for all these particular memory accesses. So the memory address uh, is divided in three different fields. In case of direct mapping, it is divided into three different fields. So these three different fields, they are referred to as the word address, the line address, and the tag address. Okay. The word address is determined by the size of the block. Okay. For example, here there are four words in a block, that is W0, W1, W2, and W3. So the word address is determined by size of the block. So how many bits are required to address this particular words in a given block? So because four words are there, you need only 2 bits. Okay. So how it is, how can you reach to the, how can you determine how many bits are required? So that is 2 to the power n. Okay, so if n bits are there, if we have n bits, then 2 to the power n is the number of locations that can be addressed by n bits. So if w bits are there, if here you can see that in the word there are w bits, then what can be the block size? The block size is 2 to the power w. Okay, so that is the word. Then line, there are r number of bits in the line field. Okay, so again this particular line field is determined by how many number of lines are there, how many bits are there in the line as a part of that particular address is determined by number of lines. So here m number of lines are there. So this r bits means if we take 2 to the power r, if we take 2 to the power r, then that will come out to be the that will come out to be m. Okay, because m number of lines are there. So to address the m number of lines, to identify one of the m number of lines, you need r number of bit. Okay, so 2 to the power r is m. So the out of this particular memory address, okay, which is the address of the main memory. So out of this, the lower w number of bits, they give the word address. Okay, the word in that particular block at which location it is. Okay, for example, here the block is of four words. So address of the first word is 00, address of the second word is 01, address of the third word is 10, and address of the last word is 11. Okay, so you need only 2 bits. If there are 8 words in the block, then you need 3 bits, that is 00021111, and like that. If the block size increases, the number of bits required will be increased. The line field gives the line number. Okay, it gives the line number where that particular block may exist. Okay, so the line number, it may, the line number may be, let us say, uh, of 4 bits, 5 bits, or 6 bits. If it is of 4 bits, then 2 to the power 4, that is, there will be 16 lines. So first line will be having the address 0000. Next line will be having 0001. That is, line number is given by the r number of bits. Okay. So what CPU does is that it first leaves this particular word address, then it selects the line address, that is r number of bits. With r number of bits, it goes to that particular line. Okay, so if that particular block is present in the memory, if a block is present in the memory, it is present at a particular line. Okay, so as we have seen that block number 0 is always there at line number 0. Block number 2m, it is again there at line number 0. Okay, so like that. So this gives the line number, and with this particular line number, the CPU first searches whether the block is present at this particular line. Okay, so this is the line number. So at this address, the block is being stored. Okay, so automatically, if we store the block at this particular address, then automatically it is going to compute. It is going to do that particular calculation. That is, it is going to uh, give you the line number of j modulo m. Okay, so it goes to that particular line number. Then at every line there is a tag. At every line there is a tag. So what is the purpose of that particular tag? This particular tag is for the purpose that uh, this particular address is called a tag. The upper bits, they are called the remaining bits of the memory address, they are called the tag. Okay. So this tag is stored at each of the line. If the tag which is stored at this particular line matches with the tag of the required block. Okay, so this is the tag of the block which is stored in the line. If this particular tag matches with the tag of the required line. So if it matches, then it is the hit in the cache. Okay, so it is called the hit in the cache, and in that case, what happens is that the word address is used, and that particular word is read from the cache directly. Okay, so if the tag matches the tag of the block which is stored at the line, and the tag of the required block matches, then the word is present in the block is present in the memory, and the word is read from the cache directly. But if it does not matches, then there is a miss in the cache. That is, the block is not there, and in that case that particular block is there in the main memory. So the address is taken from this particular uh, line address and tag address, that is s plus w. Okay, and to that the word address is added, and the word is read from this. But the word is read from this, and this block is also copied here. Okay, so as we have seen in the flow chart, that particular, if there is a cache miss, then the block is copied into the word is read from the main memory, but simultaneously the whole block is read from the main memory, and it is put into the cache memory. Again, while putting it into the cache memory, what happens? Now the new block has been put into the cache memory, and it has got the new tag word. So this particular tag word is stored at this particular tag in the line. Okay, so that if if the next word is required from this particular block, then all the words in this particular block, they have the same tag. Okay, so if you see, then the upper s minus r bits of this particular block, they are same. Okay, only the bits, that is the line number and the word number, is going to change. So for all the for all the words in a given block, the tag is same. So that is why this particular tag is stored here. So this is to identify, that is, uh, let us say at this particular block, block number 0 can be stored, or block number m is stored, or 2m is stored. So to identify which particular block is there in this particular location at this particular line, that particular tag word is stored. Okay, so this particular tag is different for block number 0, it is different for block number m, it is different for the block number 2m. Okay, because it is the upper bits of the address, and those particular bits, they are different for each of the block, and those particular s minus r bits, they are stored as the tag here. Okay, so this is how is the direct cache mapping. Okay, uh, so there is a comparator, and this particular comparator needs to compare only one address. Okay, so this is very important, that this comparator is going to compare only one tag value, and based on that particular tag value, it takes the decision whether the block is present in the memory or not. Okay, so what is the simplicity of the direct mapping cache? The simplicity of the direct mapping cache is that only one comparison is required. Okay, and uh, the tag values, they are the number of bits in the tag, they are less. Okay, and this comparison can be done quickly. You need to compare only with one tag, and you come to know whether the block is present in the memory or it is not present in the memory. Because there is, if some block is present in the cache, then that particular block uh, that particular block can be present at a particular line number in the cache. Otherwise, that particular block is not present in the cache. Okay, so these are some of the features of the direct mapping method. Okay, so the address length is s plus w bits. Okay, so all these particular bits, they are s plus w bits. The number of addressable units, that is total number of words in the main memory, they are 2 to the power s plus w. Okay, so how many, what is the length of this particular address, that determines how many bits are there. For example, if it is 32 bits, if the memory address is 32 bits, then number of words in the main memory, that is the total memory capacity, is 2 to the power 32 bytes. Okay, because each word may be of a byte. Then block size is determined by W number of bits, as we have discussed. So the uh, uh, total number of bytes in a particular block is 2 to the power W. Okay. Then the number of blocks in the main memory can be determined by 2 to the power uh, S plus W, which is the capacity of the memory, and this is the total number of, or this is the size of the block. So there are 2 to the power S, that is S number of blocks are there in the main memory. Okay, whereas the number of lines in the cache, they are equal to M, and that is equal to 2 to the power R. Okay, so R determines the number of lines. Okay, or the, if M number of lines are there, then you need to have R number of bits for the for addressing the line number in the, from this particular memory address. Okay, the size of the cache is R plus W. Okay, so this is the total size of the uh, cache. Okay, so 2 to the power R is the number of lines. So if you multiply this by the number of words in a particular block, so number of blocks multiplied by number of words in a block, that is 2 to the power R into 2 to the power W, that is 2 to the power R plus W. This is the number of words or bytes in the cache. Okay, whereas the size of the tag, so which is stored for each of the line in the cache, is s minus r bits. So these are the features of the direct mapping. The disadvantage of the direct mapping is that if you need to so this is how the example, this particular example shows how the words are stored. Okay, for example, this word is stored at this particular this is the line, whereas this particular word is stored from the main memory, is stored at this particular line, whereas this is the tag value is 00. Okay, so this is the main memory address. The tag value for the tag value this is the tag value. Okay, so the tag in hex is written here. For this, the tag value, for all these, the tag value is 00. Okay, for all these, the tag value is 16. Okay, so like that. So whenever this particular now this particular block is stored, so this particular block is stored, so the tag value is 16. So you can see here that the 16 is stored here, and the contents, they are 11235813. So that is the data which is stored, and the line number is 0001. Okay, so like that the data can be the blocks can be stored in the line in the cache along with the tag value. Okay. So the disadvantage with the direct mapping is that you have only one line in the cache where a particular given block from the main memory can be stored, because it is the direct formula and whatever line number that particular formula gives, mod formula. So there you need to store that particular block. Okay. But CPU may be using that particular block, and in that case, there is no need or there is no way other than to swap that particular or override that particular block. Okay, so if again that block is required, then there will be so-called thrashing. That is, again and again, CPU need to bring into the memory two blocks which are simultaneously required. Okay, so lot of time is unnecessarily wasted in just swapping the blocks from the main memory to the cache. So the alternative mapping method is associative mapping, which overcomes the disadvantage of direct mapping by permitting each main memory block to be loaded into any line of the cache. Okay, so the direct mapping uh, have the constraint that you can store a particular block on the from the main memory into a particular line, whereas there is no restriction in the associative mapping, and a block from the main memory can be stored into any of the line in the cache. Okay, so the cache control logic interprets a memory address simply as the tag value and a word field. Okay, so there is no uh, that is the tag value is bigger in this case. Okay, the tag field uniquely identifies a block of the main memory. So to determine whether a block is in the cache control logic must simultaneously examine every line's tag for a match. Okay, so this is though it permits to store your block anywhere in the cache line, but searching whether a particular block is there in the memory, searching a block if it is there in the cache is very expensive, because your cache can be present in any at any of the line. So you need to compare the tag value with all the tags. Okay, so you can see here that this is how you can uh, organize the fully associative memory. Okay, so this is the memory address. Memory address is divided into two different fields only. That is the word field, which is determined by the size of the block. Okay, so w number of bits, so 2 to the power w is the size of the block, and the remaining bits, they are the tag values. Okay, so if this particular address is there, then this is the tag value. Now, because your block may be transferred, a given block, if it is to be transferred into the cache, it can be transferred into any of the line. So whenever CPU needs to uh, read from the cache, it need to check whether that particular block is present in the cache or not. So to check it, it need to compare the tag word of each line with the required tag of the block, and so many comparisons will be there. That means how many comparisons will be there? There are m number of lines here. So m tags will be there for each of the line tag is there. So there will be m comparison. Okay, and of course this particular comparator, it cannot be a serial comparator. It cannot compare it one by one. If it compares one by one, then the time required for comparison will be very large, and in that case a parallel, that is, you need to have parallel comparators. That means you need to use the comparators equal to m, that is m number of comparators are required. So if there are large number of lines, then large number of comparators are required to find whether that particular block is present in the cache or not. So after comparison, the result of one of the comparison will be maybe true, that is the block is present. If the block is present, then the every comparator is representing one line, and that particular comparator will be used for reading that particular word. Okay, so the word address will be used to read from that particular line. But if it happens that the result of all comparators, if the result of the all comparator is negative, then it means that the block is not present in the cache, and the block is there in the memory. So that is the cache miss, and in that case the block is read from the word is read from the memory, as well as the complete block is read from the main memory, and the block is now stored into the cache memory. But that particular block can be stored in any of these particular lines, and in that case a suitable line is selected by the cache replacement algorithm. Okay, so though you do the block can be stored into any of the cache line, but that particular cache line should be suitably selected, and for that purpose what you need is the cache replacement algorithm. So which particular line is to be replaced by the new block is determined by those particular cache replacement algorithm. Okay, so this is how the fully associated cache works. So the disadvantage with this particular fully associated cache organization is that you need large number of comparators. Okay, so the comparison is not easy, it is very expensive. Okay, so the hardware, because this is to be done by the hardware, and it is very expensive. Okay, but the advantage is that you can store that particular block anywhere in the cache line. Okay, now you can go through this particular example later on, and this particular you can say actual uh, actual storing of the blocks in the cache. These are the cache lines. Okay, you can see here that this particular block is stored at this particular position. The contents are FEDCBA98. Okay, so they are stored in the cache line. This is the line number 1. And what is the tag value? Tag value is 058CE7. So that is the tag line for this particular middle address. Okay, so this is the tag line. So the bits except the last two bits are the tag. Okay, so again the tag is written here in the hexadecimal. Okay, so that is why we have see the length of the address in binary. Okay, so this is the binary address. I get this particular, the size of this particular binary address is so this is 32 bits, and uh, the number of hex bits here, they are 0, 1, 2, 3, 4, 5. So 2 to the power 5, it is, I think it is 32 bits. Okay, so this particular memory address, it is 32 bits. So if we want to represent the address in a compact form, then that is why we use this particular hex number. Otherwise the computers, they work only with the binary numbers. Okay, so because even the data is also written in the hexadecimal, so this is the 32 bits that is written over here. Okay, uh, so this is how is the associative mapping. Okay, uh, sorry, it is not 32, the memory address is 24 bits, That means there are how many hex digits in this 24 bits? Means there are 8 hex digit. Okay, not 8, 6. There will be 6 hex digits for required for this representing this particular 24-bit address. Okay, whereas as far as the data is concerned, it is 32-bit. So the data will require 8 hex digit to represent the 32-bit binary number. Okay. This is the summary of the associative memory. The address length is S plus W bits. The number of addressable units, they are S plus W. So it is same as that of the direct memory. That is the block size. Okay. The word size is also 2 to the power W. Okay. The number of blocks in the main memory, they are also 2 to the power S. Okay. Whereas the number of lines in the cache, so there is no restriction or there is no relation of the field in the address to the number of lines. You can have any number of lines in the cache. Okay. Whereas the size of the tag is S bits. Okay, so this is the difference. That is in the direct memory, the size of the tag is S minus R, whereas here the size of the tag is S bits. So that is the associative mapping. The disadvantage with the associative mapping is the number of comparisons very large. Now there is set associative mapping method. So set associative mapping is a compromise that exists that exhibits the strength of both direct and associative approach while reducing their disadvantages. Okay. The disadvantage of the direct mapping is that a particular given block can be stored at a particular line only, whereas the disadvantage of the associative mapping is that uh, large number of comparisons are there. Okay, so this particular problem is solved in the set associative mapping. In this case, the cache consists of number of sets. The cache is divided into number of sets, and each of which consists of the number of lines. So there are number of lines in a given set. Okay, so the relationships here are like this. That is, m is equal to n into k. So I is equal to j modulo n, where j is the number of or it's the block number in the main memory. Then m is equal to number of lines in the cache, whereas uh, I is the cache set number. Okay, so what you get here is the set number and the uh, not the line number. Okay, so there are no number of lines in a particular set. V is the number of sets. Okay, whereas the k is the number of lines in each set. Okay, so n is the you can say the number of sets. Uh, here it is written v. So, but I think here also either should have been written v. So, or here we should have used n here. Okay, so it is divided by number of sets. So you can see here that you have number of sets here. So in the first sets there are number of lines, that is k number of lines are there. This is the second set number 1, k number of lines are there. Okay, so the memory address is divided into the word address of W bits, the set address of D bits, and tag address of S minus D bit. Okay, so whenever a word is to be searched in the cache, then the set bits are used to read the tag. Okay, so the set bit will first identify the set in which the block may exist. So if the block exists, then it may exist in a given set only. Okay, so it may be at this particular line in the set, or this line, or any of the line. So only the tags of that particular set are to be compared to find out whether the block is present in the cache or not. If it is present, the result of one of the comparator will be true, and that word will be read from the specified line. If all the comparators gives the result false, then in that case it means that the block is not present in the cache, and the block is to be read from the main memory. The word will be read by CPU, and the block will be written into this particular cache, but it will be written in the specified set only at one of the location in the specified set. At one of the line in the specified set. So that particular again at which line it is to be written is decided by the cache replacement algorithm. Okay, so by dividing your cache into the number of set, what happens is that we are going to reduce the number of comparisons, and the number of comparators required in the set associative mapping, it will be less. Okay, uh, but as well as what happens is that whenever some block is to be moved into the cache, then you can move it in any of the line in that particular set. Okay, so there is no restriction that the block is to be moved into a particular line only, as like the direct mapping. Okay, so this is the way that you can use the set associative mapping, and which has the disadvantage, which solves the disadvantages of the direct mapping and associative mapping. Okay, so this is the summary of the set associative mapping. The address length is S plus W bits. The number of addressable units, they are 2 to the power S plus W. That is the number of bytes in the main memory. So it is same for all. The block size is again same for all mapping, that is 2 to the power W. That is the number of blocks in the main memory is again same 2 to the power S, whereas the number of lines in the set is K. Uh, and the number of sets, they are V, that is 2 to the power D. The number of lines in the cache are M, and the M can be obtained by multiplying the number of sets into number of lines in a particular set, that is K into V, that is K into 2 to the power D. And the size of the cache is K into 2 to the power D plus W, that is the number of lines into the number of bytes into in one line, and the number of sets. Uh, then the size of the tag is S minus D bits. Okay, so this is the summary of the set associative mapping. Okay, so you can go through this particular example of the set associative mapping in detail. For example, this particular block is stored. This particular block from the main memory is stored into the cache. Okay, so you can see the contents, they are same. The You can see the tag value is this much is the tag value. Then set plus word, remaining is the set plus word value. Only 2 bits are there for the word address, remaining is the set address. So here if we see the memory address, which is of 24 bits, then 2 bits are there for the word, 13 bits are there for the set, and 9 bits are there for the tag. Okay, so 13 bits are there for the set. It indicates that the number of sets are 2 to the power 13. So that is 2 to the power 13. Uh, you can say sets are there. Okay, whereas the uh, uh, here again you can see that the set number is given here. Okay, that is 0000 0001. Okay, and up to it exists up to 1FFF. Okay, so in that particular set, then you can use the appropriate any of the uh, location to store that particular data. Okay, so this is how is the set associative mapping. Okay, so this is the example. Okay, next is the cache replacement algorithm that we shall see in the next class. Now, if you have any doubts related to this particular mapping functions, then you can ask those particular doubts. Yes, have you understood the different mapping functions, three different mapping functions we have seen yesterday or today itself? We started with the direct mapping, then associative mapping and set associative mapping. Okay, so in the next class then we shall go with the cache replacement algorithm and remaining part of the cache, that is read write policy and the cache replacement algorithm. So that is the last part in the cache. And after that there is one more important uh, part in the memory organization, and that is the virtual memory. Okay, so after we discuss the virtual memory and this, then the memory organization will be part in this unit will be over, and what remains is the IO organization. Okay, so I hope you understood this. Uh, if not, then you may raise your queries in the beginning in the next class, and uh, now it is time. Okay, the time already it is going to be 9 o'clock. It is time to go to the next class. You may proceed for the next class. If you have not marked your attendance, just stay back and let me know your number, roll number, so that I will immediately mark your attendance. I hope all students have marked the attendance. Anybody left? Oh, someone has sent the message. Roll number 57. Okay, Siddesh, your attendance is marked. Any other? Yes, Gayatri, Sandeep, Shreyas, Liu meeting, Shubhangi, Vishal, Yash.